Let us start lecture 57. The course is on phase diagrams in single component and binary systems, and the topic for discussion is on the evolution of phase diagrams with different values of enthalpy of mixing, which is del H mix, for solid and liquid solutions. We have been discussing this over the last couple of lectures, and in fact, we have taken four main combinations. Combination 1 to 3 we have already done. Combination 1 talks about a system where solid solution enthalpy of mixing is 0, as well as liquid solution enthalpy of mixing is also 0. So, that means it is an ideal consideration. But when we talk about situation or combination 2, where we have seen that enthalpy of mixing for liquid is highly negative, whereas enthalpy of solid, that means solid solution, is 0. And the third combination we have taken, where enthalpy of mixing for solid solution is taken to be highly negative and enthalpy of mixing for liquid solution is taken to be 0. And we have used a binary system, that means two metals A and B are mixed together, and they are following a regular solution model for the solution formation. So, that is what that was actually our framework, and we have taken those three combinations. So, today we will try to address the last combination, what we have initially considered, that is when del H mix for solid will be positive, whereas del H mix for liquid solution would be highly negative. So, let us see what happens there. So, what we have done? We have taken regular solution model for the solution formation. It is a binary solution, and we have taken A and B, these are the two metals, and X A and X B are the mole fractions of A and B, and when you add them together it gives you 1 mole of solution. Okay. That and temperature and pressure we are keeping constant, and pressure is taken to be 1 atmosphere. Fine. So, that is the framework, and what we have done, we have taken delta H mix, which can be given as this, and this is omega is actually interaction parameter, you can say. It is related to the difference in bond energies, and when we try to consider solid solution, everything would be for solid solution, you can write S, and when it is liquid solution, everything would be liquid, even the compositions are to be considered, that liquid for the liquid are to be considered, and del G mix is nothing but delta H mix minus T del S mix. T del S mix has the same contribution whether we take liquid or solid solution, that is minus R X A ln X A plus X B ln X B, and then solution free energy, which is taken to be G 2, is G 1 plus delta G mix, and G 1 is taken to be X A G A naught plus X B G B naught. For solid, this will be for solid, this will be for solid, everything will be solid. G 1 is basically the system free energy when A and B are unmixed. So, these are the framework, and we try to see the variation of G 2 as a function of composition at a particular temperature, and of course, the pressure is always maintained as 1 atmosphere, and we try to see free energy hierarchy in order to find stability of a phase at that temperature, as well as when these particular diagram cross each other, we try to see the equilibrium condition by looking at the common tangent. Okay. So, accordingly we have found phase diagrams in 3 conditions. So, what are those 3 conditions or the combinations? Combination 1, we talked about del H mix or omega S equal to omega S equal to 0, and another one is del H mix for liquid or omega L equal to 0. And that time our phase diagram was isomorphous. This is XB equal to 1 pure B side, XB equal to 0 pure A side. This is TM A and this is TM B, melting point of pure A and B, and we see a plot like this, I separate plot, and here we have liquid, here we have solid, in between we have solid plus liquid. This is called isomorphous. Then second combination, we have taken del H mix for solid or omega S to be 0 and del H mix liquid or omega L to be highly negative. And that time we see that the stability of liquid phase has gone up, and these are the two melting temperatures, and we see the liquid is stable even below the melting points of both the metals. So, we have a point here. So, we form two eyes, this is one eye, this is another eye, and below this, so this is solid, this is liquid, and here we have solid plus liquid, and in order to differentiate these two solids we have taken S1 and S2, and here we have S2 plus liquid. Okay. So, remember this is temperature axis, this is composition axis, this is temperature axis, this is composition axis. Okay. And x b equal to 1, x b equal to 0. Fine. This is the second combinations what we have considered. Now, the third combination 3, we have taken delta H mix S or omega S is highly negative, whereas delta H mix L omega L is equal to 0. That time we saw the stability of solid has gone up. So, the solid will be stable even beyond the highest melting point metal. Okay. So, this is TM B, this is TM A, temperature this way, X B equal to 1, X B equal to 0, and we saw that we had 2 I, but that I has flipped compared to the second combination. Okay. So, here we have solid, here we have liquid, here S1 plus liquid, and in this zone we have S2 plus liquid. And we have seen with the help of Gibbs free energy of the solutions and composition plot, and we checked the stability of different phases with the help of free energy hierarchy as well as common tangent rule. Those are the equilibrium conditions at different temperatures. So, we saw these three combinations. In fact, we have also seen if this value is going further negative, then this plot, this particular point will shift towards downward, because the stability will further, stability of liquid solution will further go up, and in this case if this is less than 0, then this point will go up, the stability of solid solution will go up. Okay. Will expand over the composition range as well as the solid will be existing even at a much higher temperature compared to melting point of highest melting point metal. Okay. Melting point of the melting point of B. So, melting point B has the higher melting point than A in that combination. So, this particular point will go to higher temperature and this particular zone will also expand. Here also these also expand as we go lower and more negative values of delta H mix liquid. So, these we had a kind of subset combinations we have considered and we saw how to enhance when that enhancement of solid solution stability or the liquid solution stability will happen. So, now one important aspect what we have to consider. So, the difference in these two values. Let us take some values. Let us say this value is 0 and this value is let us say minus 20 okay, or minus 15 or minus 10. So, these kind of conditions. So, the difference is basically is coming out to be the difference of del H mix solid and liquid is coming out to be a very highly negative. So, that case we will experience this fine. So, this is this combination about this and this combination about this fine. Now, here also if I try to look at, we can take a value, we can take this value to be minus 15 and or I can take a combination like 0, let me just take minus 15 and this one to be 0. So, then this one to be 0 and this one to be minus 15. So, the difference solid liquid difference is going to be highly negative. So, then also it will we will have this kind of plots. So, this difference in this del H mix values also will decide the pattern of this particular plot. Let us see couple of examples with the help of some values. For example, let us say I take a situation when let us say sub combination where delta H mix of solid, let us take this is minus 15 kilojoule. So, here remember these values are in terms of kilojoule, these values are in terms of kilojoule per mole. So, these values are in terms of kilojoule per mole. Okay, fine. So, now if I take this one to be 15 kilojoule per mole and del H mix liquid equal to minus 20 kilojoule per mole fine. Now, you see the difference is not still the difference is if I try to differentiate make a difference between del H mix liquid minus del H mix solid, it is coming out to be minus 5 kilojoule per mole. So, del H mix liquid minus del H mix solid, this difference is coming out to be minus 5 kilojoule per mole. So, it is not a very high negative, not a very high negative. It is negative, but not very high negative. In that case, we have to just understand the stability of a phase enhances if the del H mix value is very negative. Why? Because that negative value along with minus T del S mix, that combination will drag the free energy del H mix value, del G mix value, the mixing free energy value will be steeper downward, okay, steeper as well as convex downward. So, that enhances the stability of that phase. Okay. So, here we see this one has a very high negative value, this one also fairly high negative value, the other one for solid, but the difference is small negative. So, in that case I have to just see that the liquidus line. So, liquidus line in case of isomorphous. So, isomorphous phase diagram was like this x b, this is T m A, this is T m B. So, isomorphous was like this I was both sides, one was this liquidus line and solidus line, this is the liquidus line and this is the solidus line. Liquidus line is actually curved convex upward and the solidus line is actually curved convex downward. Okay. But here since del H mix solid, my del H mix liquid is equal to 0, because both the values are 0 0, fine. So, that is what we get that. Now, if this difference becomes 5 kilojoule, so that means the solid compared to solidus line, the liquidus line should actually bend downward. Why? Because you have to understand the stability of liquid solution enhances. So, that means the liquid zone should expand. Okay. So, that way this particular line will actually seep downwards. Okay. So, like this a kind of situation would happen like this. So, this case, so this particular liquidus, when we have del H mix liquid minus solid is equal to minus 5 kilojoule per mole. So, I am just giving a reference, just a kind of a value wise how it senses the stability of a phase. Now, you see this was the liquidus line, this was also liquidus line, this was the liquidus line when this difference was 0. Okay. So, in order to understand the stability, enhanced stability of liquidus, this liquidus line has actually gone down. So, the I width has actually shrunk. Okay. So, that way the phase diagram will change. So, then phase diagram will change to x b, this is temperature, this is T A, this is T M B. So, now phase diagram, this is solidus. Okay. So, still I will get this is liquid zone has expanded, solid zone in comparison to liquid zone remains similar. Okay. So, this is the change what you notice in the phase diagram. Okay. Now, let us subcombination, this is let us say 1, this is subcombination 1. So, subcombination 2, let us say situation like del H mix solid still remains minus 15 kilojoule per mole, but del H mix liquid becomes minus 10 kilojoule per mole, fine. So, if that case I see that del H mix solid minus del H mix liquid is still minus 5 kilojoule per mole. So, now you see the previous case, the subcombination 1, we had other way around, the liquid has more stability compared to solid. Now, here solid has more stability compared to liquid. So, in case of isomorphous, the solidus line will now expand. How it can, solidus line will actually bend upward, and that way actually it gives an indication that solid zone expands, and expansion of solid zone also indicates the higher stability of solid solution. Okay. So, the change would be, so this was the situation where both the del H mix values were 0, x b. Remember, please do not forget to put this extreme ends composition, x b equal to 0, x b equal to 1, x b equal to 0. Here also x b equal to 1, x b is varying this way, x b equal to 0. So, this is T M A, this is T M B. Now, this is the liquidus and this is the solidus. Now, in this case this is liquid, this is solid, the liquidus solidus line will go up. So, it will start having bending upward. So, the solidus line will start moving upward, fine, compared to compared to liquidous line. So, the modified plot would be the phase diagram. So, temperature is increasing this way, this is x b equal to 1, x b equal to 0, this is T m b, this is T m a. Now, liquidous line would remain and the solidus line will bend upward. So, this is liquid, this is solid, and this particular zone has expanded. So, that is what it indicates. So, with the help of, so now sub combination 2, we are seeing that the solidus zone is actually expanding, since the difference is not extremely high, but moderately high, but still negative. Negative means it indicates the stability of the solid solution or liquid solution. So, we have seen two sub combinations, and we see how to show the stability of a solution in phase diagram when the difference of del H mix values of solid and liquid solutions is not very high negative. Okay. So, now we will take if you see the main combinations, that is 4 combinations. So, fourth combination, if I try to look at the combination 4, so we started with that combination talks about del H mix solid is positive, but del H mix liquid is highly negative. Okay. So, this combination we are talking about. In fact, we can also write in terms of omega. Fine. Now, here we will see that this one can also get greater than 0. Okay. Then what will be the situation? So, we will try to address these two situations. First, let me address this one. Okay. In fact, if we see this particular, let us say this is y, this is 1, this is 2. Now, if you recall, we have talked about the phase diagram or the del G mix or the Gibbs free energy of mixing, or in fact G2, that the solution free energy, when this one is positive. We have done it while trying to address the effect of temperature on del G mix as well as G2 of that is solution free energy. Okay. So, now let us actually draw that. If we recall, we have tried to see this one, and in fact, remember we have to take the reference now G versus T for the solid A and for the pure metal A and pure metal B. Pure metal B has higher melting point. So, this is G B of solid and this is G naught B for liquid. This is the T M B and this is T M A, this is G A naught solid, this is G A naught liquid. Okay. So, this particular reference we will take, this is a kind of arbitrary reference, we have been talking about it. Now, if I try to look at free energy variation as a function of temperature, these two are 0 0 and we are taking a temperature which is below T M A, which is definitely below T M B. So, that means here we can talk about this 0 can be assigned to G B naught solid and here G A naught solid. Okay. Then I can actually have, fine, this is delta H mix for solid. We are trying to do it for solid, and minus T del S mix we can actually reflect. Let us say this is minus, if I do it with a dotted one. So, at that temperature, if I try to see the minus T del S, then del S mix. So, let us say this one is this is let us say minus T del S mix. Now, under this situation I see that the meet point, these two distances are different. In fact, this one is more than this. So, my plot for solid free energy, solid solution free energy would be, or let us say delta G mix would be this one. So, this would be delta G mix of solid. Now, in fact, we can also write this one as G2 solid, since it can be written as G1 plus delta G mix solid, and G1 solid is nothing but 0. Why? XA GA naught solid plus XB GB naught solid. So, these two values are 0 0. So, this turns out to be 0. So, this becomes G2. Now, I see that I can have a common tangent. You apply that rule. So, I will have a common tangent. Here it becomes G bar A of solid 1 equal to G bar A of solid 2. So, these are two solids. In order to differentiate that two solids, we are putting S1 and S2, and here, so this point corresponds to that, and this point corresponds to GB bar S1 equal to GB bar S2. So, these two phases will be in equilibrium. Now, if I increase the temperature, this one is independent of temperature. So, we have this particular factor is independent of temperature. So, now we are increasing temperature and there is a minus sign. So, it will be further going down and convex downward. So, this plot would change to, so this one change to, let us say this becomes T1 del S mix, and T1 is greater than T, because del S mix is positive always, minus T del S mix is always negative. So, it will further go down. Now, we see the midpoint distance from 0 for the minus T1 del S mix is much higher than del H mix of solid. Okay. So, definitely this curve will final curve will be actually convex downward. This plot will take a shape like this. We can actually draw this. Okay. So, this becomes G2 at T1, and this one was G2 of solid, of course, of solid at T. So, now as we do it with increasing or decreasing temperature, we can get a pattern, and that pattern is reflected like this on phase diagram. This is x b, of course, this is x b equal to 1, x b equal to 0, x b is varying this way. Okay. Now, T m A, this point is T m B, and this is temperature axis, composition, x b equal to 1, x b equal to 0. Now, if you recall, we got a plot like this, and here we have S1 plus S2. Fine. So, we see, and this is the point where we reach criticality of temperature, where the inflection in free energy curve with composition is just starting. Okay. So, that is what we are actually meeting one point, and after that inflection will keep on expanding. Okay. So, in fact, if I decrease the temperature, this plot would be, if I do it with a different color, this plot would be like this. So, if I decrease the temperature. So, the temperature decrease means this particular, this dotted minus T del S mix will further shift upward, but still it will be convex downward, and del H mix for solid will be felt more for the variation of towards the variation of delta G mix of solid or G 2 mix of solid. Okay. So, and you see that this equilibrium point will shift towards pure metal side, and this indicates phase separation. Phase separation, higher temperature, these 2 points will be closer each other, and lower temperature with these 2 points will further go apart. Phase separation means this side S 1 we have AA bonds preferentially, whereas S 2 which is this one BB bonds preferentially would like to have in the system. Fine. So, this plot we have seen considering the condition 1 for a single solution. Now, if I try to take this one and let us say this one, and that time for example, we have seen combination 2 we have seen this. Okay. Now, just I am reflecting that. Now, as we increase the temperature, as temperature is increased, G 2 of solid that goes from having 2 inflection points to completely convex downward. Fine. And this convex downward nature, initially it would be shallow. As we increase the temperature, it keeps having a deeper and deeper convex downward. But if I try to compare with respect to liquid solution, which is G 2 liquid, as we increase temperature, it becomes initially, since it was delta H mix for liquid is highly negative, the delta G mix is, to start with, it is having a very high steeper convex downward shape, but as we increase temperature, since minus T del S mix will be felt more and more, this G 2 liquid will be always deep convex downward. So, it will keep having deeper and deeper convex downward shape. Convex downward shape. Fine. So, now if I try to see as we increase temperature, let us say I reach to this temperature, fine, which is below TMA, I can have a situation like this. So, this is x p going this way, x p equal to 1, x p equal to 0. Now, we had this plot S 1 plus S 2. Now, we can have a situation like this. This is T M A, this is T M B, this point and this point. Okay. Now, since it is actually because of these two conditions, it is similar to this. So, if I try to plot that, we will get a plot like this. Fine. So, this is liquid and this side would be S 1 plus liquid, this side would be S 2 plus liquid. So, now we get a plot like this when del H mix is greater than 0 and of solid is greater than 0, del H mix for liquid is less than 0. Fine. And it is such a positive value that this peak point ends before this point arises. So, there is a gap. So, we have everywhere we have solid, and in between this dome we have phase separation, and beyond that we see equilibrium in such a fashion what we have seen in this situation. Okay. So, that is what we are just combining 1 and 2, this particular two situation, one situation and another situation in such a fashion that it actually turns out to be this at a higher temperature, fine, and that is what we are having such phase diagram. This is T, this is X B, this kind of phase diagram will arrive at. Okay. Now, we have to see, we have seen that initially we started with this particular pattern, this one. Now, if this value is actually taking this, then what would happen? We have to see that. So, there becomes we have to see how it turns out, or we can say combination for B, and let us say this one was let us say combination for A, this particular one. Okay. So, if I take that combination for B, we have to take delta H mix to be highly positive, and delta, this is solid, delta H mix for liquid is highly negative. This is the situation. If I want to put some values, let me put that values. Let us say I put this value as plus 10 kilojoule per mole, and here let me put this value as minus 10 kilojoule per mole. This is a kind of arbitrary combination. So, that case I have to see what is happening. This is let us say 1, this is 2. Now, if I try to look at 1 combination B of 1, I see this is the phase diagram. I am getting this is the phase diagram. This is the phase diagram S1 plus S2. Temperature X B is varying this way, X B equal to 1, X B equal to 0. And if I, and this is definitely, this is Tm A, and let us say this is Tm B. Let us say this point is Tm A and Tm B. Now, if delta H mix solid is gradually increasing, okay. So, if it gradually increasing, that means as per this particular plot, this value will be farther upward and convex upward. Okay. So, hence much higher temperature it will be needed to bypass that inflection point in free energy of solution, and then it becomes completely convex downward. So, higher temperature will be needed. As we increase this, with increasing temperature, this particular plot will actually go up. So, the expansion of this phase separation zone will increase as we increase this, okay, because this inflection will keep appearing at higher and higher temperatures. So, the plot would be like this, and then it becomes like this, then it becomes like this. Okay. So, this kind of situation can arise. So, we see now this particular temperature zone, this is one temperature and this is another temperature, this dome is actually expanding higher and higher temperatures. So, what does it mean? That even at a temperature which is beyond Tm A, okay, of course, it is less than Tm B, even that condition we can have a plot of G2 of solution of solid solution would have two inflections in that particular pattern. How? Now, if we take this, then this 0 0 point, this would be GB naught for solid and this would be GA naught for liquid. So, this particular point would be GA naught for solid. So, it will be closer to that. You just check that particular pattern, free energies for pure A and B. This would be GB and then place these values accordingly. So, this will be solid and liquid. So, now solid G1 line would be, this is solid G1. So, I can put this one as dotted, this is G1 solid and liquid would be this is G1 liquid. Now, at temperature let us say we are considering this or let us say this. If I try to draw only the solid solution free energy, it would have a pattern like this. Okay. So, like this and then this is the common tangent. Okay. And here this one is G2 of solid. G2 of solid. So, we see two compositions which is XB of S2 and XB of S1. They will be still be there. Okay. So, these are the 2 points of these 2 points. Okay. But in the meantime, if I see the liquid line, liquid solution line, that also would have its existence. Okay. So, now that existence can actually take this one from here it will start. So, you can have a situation like this. Liquid. Okay. I can have a situation like this. Okay. So, that time I have to see at what point this particular line, the two tangent, this tangent and if I see one more tangent here, let us say I can draw one more tangent here, one more tangent here, I see one more composition, they will be under equilibrium. So, I have to see at what moment these two tangent will merge each other. Okay. And that thing happens as we keep moving upward. Okay. So, now this moving upward means means as a function of as we increase the temperature from low temperature to high temperature, this situation can arise at some point of time. Okay. Let us see that part. So, this is my reference T G, this is G B naught solid, this is G B naught liquid, this is G A naught solid and this is G A naught liquid. This is T M B, this is T M A. This is the reference we have to take. Now, let us say I take a temperature, which is below T M A, and I am taking that temperature in such a fashion that the liquid free energy line will lie above the solid free energy line over the entire composition range. So, that means very low temperatures we are taking. I will just draw it and you just take the reference. This is G1 for solid, this is G1 for liquid, okay. So, this is G2 solid with the condition which is combination 4B, or I can write del H mix solid greater than 0, del H mix liquid less than 0. So, this is at temperature T1, let us say. So, I can take the plot here. T x p is varying this way, x p equal to 1 and x p equal to 0. So, this is T m b, this is T m a. Let us say this two values, this is T1. So, now we see two terminal solid solution, these 2 points. Now, as I increase temperature, now temperature I am increasing. I am still T2 is greater than T1 and Tm is still greater than T2. So, I am increasing temperature. So, this is definitely Gb naught solid, Ga naught solid, both will be 0 0, x p equal to 1, x p equal to 0, x p varying this way. Now, as we increase temperature, this gap will shorten. So, this is Gb naught liquid, this is Ga naught liquid, this is liquid G1, this is solid G1. Now, solid line now could be, so as we increase temperature, so this point will shift towards left. Fine. So, these are the two compositions I am showing here. Okay. These are the two solid compositions, x p solid 1, solid 2 right side, x p solid 1. So, now as we increase temperature, these 2 points will come closer to each other. Okay. So, now I can have a common tangent. Here also I did draw a common tangent. Now, I am not giving those marking, you know that the chemical potential or the molar partial gives free energy of A and B in those two solids will be equal, both the components. So, one case I am writing, but rest of the case you just keep putting that values. This is Gb naught for S1 equal to Gb bar for S2. Similar way, this point would be, this is the point, and this point Ga bar of S1 equal to Ga bar of S2. Fine, like that way it happens. So, this is a common tangent, these two compositions Xb S1, Xb S2. So, now at temperature these two compositions are put here and one is here. So, this one can be placed here and here, but definitely these two compositions will shift towards each other. Fine. Those are the two solid compositions. So, this is at T2. Now, we have a temperature, this temperature is a, and of course, we have to show the liquid one. Liquid one now can actually go like this. This is G2 liquid, can actually crisscross, but we see the lowest, the tangent, common tangent value, which is the free energy of the equilibrium phases, is lying far below the liquid solution free energy. So, that means the stable phase would definitely be these two compositions of solid 1 and solid 2. Now, if I go for the third combination, third situation. So, the third situation, let us say I want to do it, still it will be G 1 solid. Okay, this is 0 0, G A naught for solid, this will be G B naught of solid, these 2 points G B naught for liquid, and this is G B naught for G A naught for liquid. Okay. Now, the liquid G 1 is here, liquid, and the solid G 1 is here. Now, I have a situation like this. A situation would arise T equal to T 3, which is still less than T m A, such situation, and that time, because we could see that as we go higher and higher temperature, this liquid line will actually shift downwards, convex downwards, because minus T del S term, del S mix term will actually be felt more in order to take the particular, this is G 2 of liquid line, further downwards and convex downward, steeper, it will keep getting steeper, as we have said before. Now, we have a situation where I can have a common tangent, and that common tangent will pass through all 3 points. So, this is the one we get. Okay. Now, we see one plot, this is x b of liquid, this is x b of solid 1, this is x b of solid 2, and here now I have to write those conditions. Here would be G B bar of liquid would be equal to G B bar of solid 1 equal to G B bar of solid 2, and at this point G A bar of liquid would be equal to G A bar of solid 1 equal to G A bar of solid 2. So, that means all 3 phases will be under equilibrium. Okay. And we can actually pinpoint those points over a temperature T 3. So, let us say this is my T 3, and I get those compositions. One would be, this is the liquid one, this is the solid one, this is another solid. So, I can place it little on the, so I can place it here and another one is placed here. So, this compositions. So, now this is XBL, this is XBS2, this is XBS1, but all those compositions are different, but all those phases are in equilibrium as per the common tangent rule, and exactly such situation will arise. Now, if I increase the temperature further, let us see what happens. Now, if I increase the temperature further, so if I increase the temperature further, let us say I reach to a temperature which is T equal to T 4, but below T m A, I can have a situation like this. Let me just draw this, then I will start explaining. Okay. This one G2 of solid and G2 of liquid would be like this. Okay. This is G2 of liquid. Now, I see that I can actually have two tangents. One tangent is here, another tangent is passing through like this. So, if I extend this, I will get an extension like this, another extension is here. So, now this point indicates equilibrium between G A bar solid 1 is equal to G A bar liquid. This point is G A bar S 2 equal to G A bar of liquid. Here G B bar of S 1 equal to G B bar of liquid, and at this point G B bar of S 2 equal to G B bar of liquid. So, now we have four compositions. One composition is here, another is here, here is one more, here is one more. So, those compositions are X P S 1, X P liquid, but this is X P liquid again, and this is X P solid 2. Now, this can be actually written as X P S 1 in equilibrium with liquid. This can be written as X P liquid in equilibrium with S 1. This can be written as X P liquid of the solid the composition of liquid in equilibrium with S 2, and this one can be written as X B composition the solution 2 composition in equilibrium with liquid. And now, we have between these two, we see the liquid has the lower free energy compared to any other free energies. So, the liquid will be stable. Between these two, we have equilibrium between S 2 and liquid. Between these two, we have equilibrium between S 1 plus liquid, and existence of liquid and solid S 1, and here solid 1 solid 2 plus liquid. Now, right side of it we have S 2, left side of it we have S 1. Like that way, all those composition can be dragged to the plotted on that T4 line actually. So, this is let us say T4 line. Okay. And what are those compositions? Now, you see the solid 1 equilibrium line equilibrium point at T3, and if I increase the temperature to T4, this is at T4, this is G, this is X B equal to 1, X B equal to 0. At T4, the equilibrium composition of S 1 has actually moved towards left. Initially, as we started at a lower temperature T1, and as we go higher and higher temperature, the S 1 composition is actually shifting towards right, S 2 composition was shifting towards left. Now, S 1 composition has started shifted towards left as we cross T3. Okay. So, now this composition S 3 composition is let us say here, this is the S 1 composition of X B S 1. Now, liquid will have appearance. The liquid composition let us say in equilibrium with that is let us say here. This is the point X B of liquid. Now, another this point also will shift towards right. So, this would be X B of S 2, and the liquid line would be liquid equilibrium composition would be here. So, this is X B of liquid. Okay. So, now I see that at T4 I am getting 4 equilibrium compositions, and we also see from the free energy composition diagram here X P is varying in this way. Free energy composition diagram, I see that what phases will appear as a stable phase at temperature T4 from free energy composition diagram and common tangent rules. as well as of course, free energy hierarchy, okay, or gives free energy hierarchy. Now, at T m, T equal to, let us say I am considering T equal to T m. Now, that case, let me just draw that. This is 0 0 G B naught solid, here G A naught solid as well as liquid, both will have same free energy, and that is assigned, that is 0 is assigned to that. Now, here it will be G B naught for liquid, this is liquid G 1 of liquid, and liquid free energy line would be steep downward, and the solid line would have like this. So, this is G 2 of solid, this is G 1 of solid. X b is varying this way, x b equal to 1, x b equal to 0. So, that condition I will only have this, here we are having merger. So, now at this particular point we have solid and liquid pure A would coexist. Now, that can be taken as liquid line as well as solid line, fine, because here the free energy of G 2 of solid and G 2 of liquid, they are merging. But on the right side we can still draw a common tangent. Okay. So, now we get one composition here, another composition here. So, this solid 2 composition is still drifting towards right. So, this is X B S 2 and this composition is X B liquid, and corresponding equilibrium condition you can write down. Okay. Now, here T m, now we have the solid composition will shift towards right, but the liquid composition will also shift towards right here. Okay. So, this is X B L, which is in equilibrium with S 2, and this composition is X B S 2. Okay. This is one, and then if I keep moving towards higher and higher temperature, T m A, please that you modify, this is G, and let us say I take a temperature which is in between T m A and T m B. This is T 5. Okay, fine. Yes. So, this is T 4, this is T m, this point, this one, and this one is T 5, T 3, T 2, T 1. At T 5, we have a situation like this. Still it will be solid. Now, it will be liquid, solid, 0 0 point, x b is varying this way, this is x b equal to 1, x b equal to 0, this is G axis, this is composition axis. Now, I can put it in a dotted fashion. Now, G 1 of solid is this, and G 2, G 1 liquid is this. Now, I have this, and now you see this particular pattern slowly will die out as we increase temperature. You refer to the earlier discussion. So, this one would be this G 2, this is G 2 of liquid, and G 1 of G 2 of solid would be okay. This is G 2 of solid. Now, we see a common tangent. The common tangent common tangent will pass through this. So, this should be xp liquid and this should be xp solid 2. So, here also I can have two compositions. So, this composition will, this is xp, is this one I can, okay. So, I can actually, this composition I can take it here. So, this is Tm. Now, here this solid composition will be lying here. Now, as we come to T6, this is T5, we are going T5. So, this is T5, T5 which is less than Tmb or greater than Tma. So, that situation, I have a similar situation like this, but the composition will shift towards right also. So, this, the liquid composition will be here and the solid composition will be here. Okay. So, these 2 points. Now, gradually as I go to T equal to Tm B, so then 0 0, this is G B naught solid which will be equal to G B naught liquid and here G A naught liquid and this point would be G A naught solid. So, we will have a plot like this. So, this is G 1 solid, this is G 1 liquid. Now, liquid line will be steep downward and the solid line might lose the entire this inflection. Okay. This is G 2 solid. So, we have all other compositions, we have liquid to be stable, but at x b equal to 1 we have pure B and pure solid will have coexistence. So, this is x b equal to 0, x b is varying this way and this is G. So, if I, this is let us say T equal to Tmb. Now, at T equal to T5, where we see that except those two common tangent left to that particular composition we have liquid stability and right to this composition we have solid 2 stability. Okay. You just follow the rule that left to this composition we have liquid line, which has a lower free energy compared to the solid line. So, that way that liquid will be stable. So, here at this point we have the merger of solid and liquid line actually. Now, we connect the pink line. So, here also pink dots, so here also there will be a pink dot. Okay. Pink dots are basically compositions for liquid in equilibrium with solid 1 and solid 2 and here also there will be a pink dot. So, now if I connect them, so this is pink line is connected, fine, and the black line if we connect this one and another one is this and here also we have one, here also we have one and in between we can actually make a solid line. Why? If I go to the situation here where T3 where 3 compositions are falling on a single common tangent, that actually indicates that between these 2 composition we have solid and liquid phase together and we have 2 solids and any composition you take between this they will break into 3 phases. Okay. So, we will discuss about this in our later lectures, but we get a kind of phase diagram like this, okay, which actually is nothing but eutectic phase diagram. So, as you see this eutectic phase diagram, here we as per our free energy composition diagram analysis, this field contains S1, this field contains S2, this between 2 pink lines we have liquid and between this S1 and S2 line we have S1 plus S2. So, those the phase zones I have marked. Okay. Between this, here we have solid 1 plus liquid, and here we have solid 2 plus liquid. So, we will discuss more about this. We see how we get eutectic phase diagram, provided that del H mix for the solid should be fairly large, as well as del H mix for liquid should be fairly negative. Okay. That combination we have such situations, but if del H mix solid is small positive and del H mix for the liquid is fairly negative, that case we might have situation like this. This kind of situation we may end up, this kind of situation. So, now with this understanding, we will consider few more combinations and see how it appears. So, as of now what we have learnt is basically we are getting a equilibrium phase diagram for eutectic. Okay. So, we will talk more about this eutectic phase diagram, and that appears when we have fourth combination, but in that fourth combination we talk about combination 4B, where del H mix for solid is fairly large and del H mix for liquid is fairly negative. That combination we have this. Okay. So, let me stop here, though these lectures are getting little longer, but you know, in order to have a complete discussion comparing other situations, I had to take little more time on these kind of lectures. So, please try to understand, try to follow these lectures, you will get to know the crux of drawing phase diagram using free energy composition diagram. Let me stop here and we will continue in our this kind of discussions in our future lectures. Thank you very much.